And here I'm going to put mu k delta to stress that I'm working in the quiver, in the mutated quiver, mu k delta, and this is k to j, u, I, u, j prime. So far so good? Yes? Because anyone wants to finish the exercise now? Please raise your hand. It's almost there. I know what it is. I know what's this guy. It's just this guy, right? Right? And I know that these primes are all the same. This is, let's say, these are all the same as before, except except the kth one that is really actually new. All the other ones are just the same. And here, since I don't have loops, I can actually erase the primes, because they are like the same here than here. They're just the same. And now, well, since I'm mutated in k, the arrows going from I to k in this mutated quiver coincide with the arrows in the original quiver that go in the other way, right? Right? And ui plus the arrows uj k, I'm sorry, I to k, k to j. I should invert it, so this should be, this goes all the way around, and this k, yeah, it should get that way, j, right? In the quiver, because you know, like, if I have my quiver, the first quiver, I see some arrows going in this way. Then in the mutated quiver, I will see just the arrows going in the opposite direction, but just the same number of arrows. And here, I can just relabel this I is just an index. I just change it for j, and this j is just an index. I can just replace it by I. And uk, it's this guy, so it's the same product. ui plus uj, the arrows going from I to k, arrows going from k to j in my quiver delta, and over uk, and these guys are the same, and this is uk, right? So said in other words, this binomial that I see, it's the same, just like it just comes like, when I apply the formula, it just comes like in the other order. But since addition is commutative, it doesn't matter. These just cancel out, and you know, I do the sandwich rule, and then I get like UK. Yes, yeah, because that's a very good question. This proof will also hold for the case of matrices. So I said that I have a matrix mutation formula. So I say that the mutation of this matrix, it's just, well, I let this to be matrix Bij prime, and B, it's my matrix Bij, and Bij prime, it's equal to minus Bij if I it's equal to k, or k is equal to j, and it's Bij plus the sign of Bik times the maximum of Bik, Bkj, and 0 in other situation, right? Why do I know? I don't know this formula by heart. I'm just deducing it as I'm writing, because I know that if this was a matrix associated to a quiver, this just means that I invert the arrows. And this is just like, given some arrows, you just add like composite arrows. And this term is telling me whether it's possible to compose them or not. If it's negative, this means that these arrows are not composable. And this sign is telling me whether the arrows should be put in that way or in that way. Yeah. So that was like the form. And I said that this, okay, like if I have now a seed, that it's skew-symmetrizable, right, like this, and I want to mutate it, then I just mutate the matrix and add a new cluster, and this new cluster, it's as before, just given by replacing or exchanging a single variable in the original one by a new one, and and by a new one, and this new one should be given like by a generalization of this formula. And what I have to do, if this is my matrix, suppose this is my matrix, B, and this is the kth column, so I see B1k, B2k, Bn plus mk, okay? So I have to focus my attention in this column and look at which entries are positive and which are negative. Some might be 0, but I just have to look which ones are positive, which ones are negative, and form two monomials out of the positive ones. Well, a monomial out of the positive ones and another monomial out of the negative ones. So this would be the product of the i's such that B, I, K, it's positive, and then I have like a monomial BIK, and then I have to still look at that column and look at the J's such that B, JK, it's negative, and I put UJ to the minus BJK. Okay? So I think here I did it, I wrote it like, I put K first, so I was looking at the row. I wanted to clarify that that was a typo in my expression. And here I put UK. So the only thing you have to do is to look at the column of the matrix. So for example, if your matrix looks like, I don't know, whatever I have, and then I have like I don't know, 5 minus 2, let's say it's a 5 times 5 matrix, 3 minus 1. What I have to look, it's at this guy, and the monomial would be U1 to the 5, U4 to the 3rd, plus, so this, I'm just looking, this is the positive summand, and then I look at the negative ones, and this would be U2 to the minus 2, U5 to the 1, I'm sorry, right? And then here I'm mutating in 3, say, this was 3, okay? So I just have to look at the column, and I just like see what's positive, see what's negative, and make a positive monomial and a negative monomial. Very easy. Very easy. There's no rocket science here. It's just positive and negative, deciding what's a positive number and what's a negative number. No more than that. Okay? So, perfect. Now, I was asked a question at the end of the lecture, and I noticed that there was like a space for confusion yesterday with the linking diagrams, because, yeah, so, does that answer your question? Okay. Let me now just say a comment between the linking diagrams. So the linking diagrams are diagrams that are there in mathematics since a long time. And then, first of all, first correction is that I draw Bn to go the arrow this way. It actually has to go this way. So first correction to what I said yesterday. Second correction is that this is not a double arrow. This is not a quiver. This has to be think as something different from a quiver. Actually, what I would like to, so let me go back to now to the, so here, for example, you have like the Wikipedia page, and here you find like the thinking diagrams, and there are like, you know, very, lots of generalizations of these thinking diagrams. So somehow what I want to convey is that this diagram, everything can be just put in the language of matrices. So this diagram is meant to represent this matrix. So we can forget about diagrams and only work with matrices. So this guy, it's just, you know, the Bn, I have here 1, 2, and I will have n here. It's just a shorthand to describe this matrix. That's a better way to think it. So this guy, for example, B2, corresponds to this matrix, 0, -2, 1, 0. And the double arrow, if I have a quiver that looks this way, 1, 2, this corresponds to the matrix 0, -2, 2, 0. These two things are different, right? So thank you for the question that was asked. Yes, because it's not the same. This is not to be thought as a quiver. It's just like the usual diagrammatic description of the diagrams. In our language, this guy, let's say this B2, should be just thinking that it's representing this matrix. And now I want to show you explicitly how the cluster structure looks like, and to compare it how different it is from the, so let me just give names. This is the B2 example, and this is the Kronecker quiver. Kronecker quiver. It's called the Kronecker quiver because in the language of quiver representations, this quiver is codifying a linear algebra problem posed by Kronecker a long time ago. So that's why it's called the Kronecker quiver. And I'm going to compare both. So here, what I did, it's like try to, you know, start with an initial seed of type A2. And then I start mutating. So I mutate in direction 1. And as you can see, I have to look at the first. I'm mutating in direction 1. So I look at the first column. The first column has just a 1 in the second row. So that's why I have a next to 1. And since I don't have negative summands, I have a 1 here. And since I'm replacing 1, I put here 1 below. Now, the next one here, I'm mutating in 2. So I should look at this seed. And you have to look at the second column because you are mutating in 2. Since you are mutating in 2, you are taking second power of something. That's why when I mutate, I start having like this 2 power of 2 here and this 2 here. And also like immediately I will get a Laurent expression. If I mutate again, okay, this is behaving weird, okay. Let's just put it like this. So if I mutate again this in 1, the matrix will just change signs. That's easy because there are no, the second case, it's empty. So I just have to change the sign of the matrix. And here I have to replace this guy by another one, and I replace it by the, I have to replace, so I hit mutating 2, I'm mutating 1, so I have to replace the first one by another one, is this guy, and I obtained it by doing this computation. So again, if I would do like the formula, I will get this expression, and you see again that this cancels. So I see like an instance of the Laurent phenomenon, where the polynomial that it's in the bottom cancels out and gives rise to a simpler expression. and it has positive integers. So it's like an example of the positivity of the Laurent phenomenon. Then, if I mutate here too, this gets more complicated because I have to look at this second column. So I have to raise this to the square, I have to add 1, and I have to divide by this. If you do that, all this, you will get this polynomial. And again, this guy, it's divisible by this guy, and it simplifies to this guy, right? So I get this seed, and if I continue, I get this seed, and if I get back, I get to this seed, right? So this is an example of a type B2 cluster algebra. So these are all the possible seeds that I obtain, okay? The question again is why this is helpful. Well, a posteriori, the answer is like, these are generators of a certain variety that it's important in algebraic geometry, and that I'm not going to describe. Second answer, it's like these polynomials are codifying elements of, well, certain invariants of categories of quiver representations that I'm not going to discuss. Maybe in the last lecture I will say a little bit about that. But yeah, so that's some sort of the interpretation that can be given to these things. And as you can see here, the periodicity is of order 6, right? So let me just compare it with the A2 example that we have studied many times. The A2 example, I started with this. Now I'm using matrix notation, not the quiver notation. So instead of writing this quiver 1 goes to 2, I'm just writing its corresponding matrix, and I'm just mutating. And here I have a pentagon. I have a 5 recurrence, but the observation I really want to stress that it's also a point of confusion is that here the x1 appears in the second entry, and if I mutate, the x2 will appear in the second entry. And also, if I mutate this matrix, I would get -1 in this entry and 1 in this entry. So here, I'm not using only mutation 1 to go to this matrix, to go to this seed. I'm also using this relabeling, this permutation. I'm permuting the indices 1 and 2 everywhere in the variables, in the variables I see, and I'm permuting the first and second row, and then the first and second column. If I apply mutation 1 and that permutation, then these two guys are equal. Okay, so let me just compare this cluster structure of type B2 with the cluster structure on the Kronecker quiver. So the Kronecker quiver does not appear in the finite type classification, so I would expect to have an infinite number of variables. Let's just get a feeling of, try to get convinced that we indeed have an infinite number of variables. So I will just draw the Kronecker quiver. So unfortunately, this software only works for the quiver case, not for the skew-symmetrizable matrix case. So all the computations, I had to do it by hand. These computations, yesterday was like just computing them by hand, unfortunately. There are other ways to do it. I mean, by a technique called folding, but that's a different story. So questions for the moment about the B2 example? Questions, observation, comments? No? Okay, everyone sees like the Laurent phenomenon and the positivity of the Laurent phenomenon in the examples? Yeah, so the Laurent phenomenon is like the denominators are only monomials and the numerators are positive integers, okay? So let's check this Kronecker quiver. This really is like the Kronecker quiver, and I want them arrows to go from 2 to 1. So let me just be strictly okay. Let's just take that quiver, the Kronecker quiver, and then I will activate the cluster variables, okay? So I see here my initial cluster, x1, x2. So let's mutate, say, in 1. So if I'm mutating 1, now my new cluster is this. I replace the first variable by this guy. And as you can see, well, it's exactly what I would expect. An empty product and this term that it's related to the 2 arrows in the quiver. And then here is the variable I'm replacing. If I still go further, I see this huge expression, and then I will just start doing that. Then my new cluster is this one. My new cluster is this guy, it's this 2, and then I can mutate in 1, and then my new cluster is this guy, and I mutate in 2, and in 1, and in 2, and in 1, and in 2, so on and so forth. So as you can see, it doesn't seem to be getting simpler. The expression seems just to get more complicated. And just to get an idea of why this is infinite type, let's look at the denominators. The denominators here were x1 to the 0, x2 to the 0, both. Here x1 times x2 0. This is x1 square, x2 square. This is x1 cube, x2 square. This is x 1 4, x2 to the 3, right? So I see a pattern. Right? It's always x1 to the r times x2 to the r minus 1, right? So, and the pattern just goes on and on. The numerators just get way more complicated, but I do see a pattern in the denominator. So I hope this pattern in the denominator kind of helps you to at least be convinced intuitively that this is of infinite type, because I will just be getting more and more and more complicated expressions, but I have an idea of how the denominator is changing. Notice, however, that the numerator is way more complicated and it's way more difficult to kind of imagine how it's changing, right? It's possible. There are formulas. There are going to be topological formulas and categorical formulas to understand. Well, there are many formulas. I mean, let me just make a small digression. So one of the main problems of cluster algebras, it's like, there are two main problems in cluster algebras. Two main problems. So one, it's let x be a cluster variable, be a cluster variable in the cluster algebra associated to B, to a matrix B. So I know by the positivity of the Laurent phenomenon that this is a polynomial in my variables x1 to xn plus m, and then the denominator is just a monomial x1 d1 times xn dn. So problem give a closed formula for the polynomial p the x1 to xn, and the vector d1, the denominator vector dn. Okay? Here, it seems like I can easily describe the denominator vector, right? The denominator vectors for these guys, it really seems like are like r minus 1. And I also have to, here I started mutated like in my tree. In that example, I start in the initial cluster, and then I mutated in 1, I mutated in 2, I mutated in 1, I mutated in 2, and here I kind of know the denominator vectors, but then it was missing what's going on when I go to this direction. So it's just going to be the other way, like the higher power would appear in x2 as opposed to in x1. So if I go to the other direction, I would have like x1 to the 8, x2 to the 9, for example. So in this example, the denominator vectors seem to be more tractable. But what about the polynomials? Can you give me, I tell you, okay, this is your tree. Your seeds are indexed by the vertices of this regular tree, and the vertices of this regular tree are parameterized by the integers. So say I give you an integer, 10,000. Can you describe the cluster associated to that vertex? So you have to give me a denominator vector and a polynomial. Well, it is possible, but in order to do that, one needs to use heavy machinery. And there are three main ingredients that one can use. The first one is topology and combinatorics. The second one is category theory and representation theory. And the third one is algebraic geometry and enumerative geometry. Okay? So three main approaches can be done using representation theory, rep theory, representation theory plus category theory. Another one is topology plus combinatorics. And the second one, it's algebraic geometry plus combinatorics. So giving a solution in these terms would require at least like 3 or 4 lectures. I mean, maybe the easiest would be this, and I would need like 2 or 3 lectures. Then it's this, and I will also need like 2 or 3 lectures, but I will also need like you to have some knowledge. This would be way more complicated. This would require like, I don't know, like some 10 lectures or something to explain this. So it is out of the scope of this mini course. I just want you to see that this is a natural problem, and it's not an easy one. You can see how even for a very simple quiver, we're trying to describe very complicated polynomials, but it is possible, okay? It is possible, and lots of the research, in this direction has been carried out in the last 20 years. The second problem, here, it's, I might just put it here. It's like, give a global model for the set XQ. What do I mean by this? In order to produce these guys, I'm just iterating, and you want to say, okay, I don't want to iterate. I don't want to, iterating is like, you start somewhere, and locally you move. So it's like a local description. So it's like, you don't want a local description, you want a global description of the pattern, right? You want a global description of the pattern. And the lecture today is going to be an example of how to do that. Here, my examples are intended to give you like the global picture. For example, this hexagon gives you a global picture of the B2 cluster algebra. This pentagon gives you a global picture of the A2 cluster algebra. I also put here C2. C2, it's an example, something that I should have corrected last lecture. It's that Cn has the diagram like going in this way. And Yeah, so Cn, the diagram goes in that way. And again, this diagram is just intended to represent this matrix, okay? This matrix. So here below, I already gave like a global description of a cluster algebra of type C2. Okay. Here it is. It's also, I have like a periodicity of order 6. And I already put here like some of the computations made to get this formula. So how I get the non-trivial cancellation. Okay? And finally, the G2 example should be written in this way. This is to be thought not as a quiver with 3 arrows. This drawing is it's meant to codify this matrix here. And here as you can see, all these drawings are a little bit charged. There are too many information here. There is too much repetition, right? Here, for example, I'm repeating this huge variable. I'm repeating it here. And this huge variable, I'm also repeating it here. So there's like a lot of repetition, right? So there's a more economical way to describe things that it's as follows.
In that case, then the linking diagram will remain same, or will it change? For example, for B2, you like define all the things. So then in that case, the linking diagram will remain same, or will there any change in that?
Would be what? In that case, the linking diagram would be what?
Will remain same, like the notation for them remains same, or will it change?
So, and the only one that it's missing is the F4, but it would be like, you know, like in the middle you will have like maybe 0, 2, minus 1, 0, or something like this. So it was the only remaining case. What I wanted to put here, it's all the possible finite type examples for matrices of size 2 by 2. All of them. I already have A2, B2, C2, G2, and there's still one more that I will show. So definition, the exchange, okay, let be, okay, so now, okay, recall from the last, okay. Recall that the periodicities of a cluster algebra does not depend on the frozen part of the matrix. So remember that I was thinking about rectangular matrices now, and here I have B, and here I have whatever. This is size n, this is size n, and this is size m, and m is greater or equal to 0, and B is skew-symmetrizable. Okay? That was like the picture. Associated to a guy, I have a cluster algebra, and it doesn't matter where I put here in the star, the periodicities would be the same. So, definition, the exchange graph, the exchange graph associated to such a matrix is the graph whose vertices are the seats of the cluster algebra And here, so here in this example, I want this pentagon to be the exchange graph. I want this hexagon to be the exchange graph. I want this hexagon to be the exchange graph. So what I'm doing is just putting the vertices. In the vertices of the graph, there are the seeds, right? But notice that in the A2 example, I was also using like this permutation. I was using that permutation, so the seeds of A considered. So that's why I'm going to put this phrase, consider up to simultaneous up to the action of Sn in the indices of x1 through xn plus m, Sn plus m, and the, Sn, and the on the simultaneous permutation of columns and rows of the matrix. Okay, so I'm just going to identify, just like in this pentagon, I want to, for example, in the example, this seed it's equivalent to the seed x2, x1. Let's say this is the vertex 1, this is the vertex 2, and this is the vertex 1, and this is the vertex 2. I here use the permutation 1, 2. Yeah, so I change vertex 1 by vertex 2, and I change the index 2 by 1, right? Okay. Okay, and edges. Okay, this was a comment. So the exchange graph has vertices and edges. I'm already telling you what are the vertices. The edges are just like, mutations plus this action, right? Like edges of the graph appear when two seeds, two equivalent classes of seed appear when two seeds are related by mutation. Right, so here, when I say like the vertices are the seeds considered up to this action, another way of saying it's like this action is just giving an equivalence relation, and the vertices are actually equivalence classes. Yeah, so if you want, all these vertices are the equivalence class of this seed up to this action of changing the numeration of the indices and permutation of the columns and rows of the matrix. Okay, so these are the examples of the exchange graph. Here I have an exchange graph for the A2. Then the hexagon would be the exchange graph for B2. The hexagon will also be an exchange graph for the C2. And I will see that the exchange graph for the type G2, it's going to be an octagon, right? So this is the first definition. And the second definition is the one of the cluster complex that I want to show you in a second. Okay? definition. Definition 1, it's two cluster variables in A, B tilde are compatible if there exists a cluster that contains both of them. So for example, these two are compatible. These two are compatible. There's a cluster containing both of them. These two are compatible. Those two are compatible. Those two are compatible. There's a cluster. But for example, this guy and this guy, oh my gosh. Anyways, this guy and this guy are not compatible because there's no cluster that contains x2 and the one that has denominator x1, x2. These are not compatible, okay? The cluster complex, definition 2, the cluster complex associated to B tilde is the simplicial complex whose vertices are the cluster variables and simplices are sets of compatible cluster variables. So it's like somehow dual to the exchange graph. In the exchange graph, in every vertex I have to have a complete cluster, whereas in the cluster complex, in the vertex I have to have a single cluster variable. Okay? So let me give you an example of the cluster complex of type C2, yes, G2. So here, as you can see, I motivated this discussion by saying these drawings have too many information. I can be more economical in this. So I'm going to do this in this G2 example. So in this G2 example, again, the corresponding matrix B tilde would be equal to B because there's no frozen part. And it's going to be this matrix. Now, the initial cluster variables are cluster variables, so there are vertices of the cluster complex. And here I just put the cluster complex. The cluster complex, it's going to be this also looks like a graph. It's like x1, x2. These are cluster variables. I put an edge because they are compatible. I put an edge because there's a cluster that contains both of them. So if you want, this edge would represent like the initial seed, right? Now, here x2, it's actually going to be compatible with two things, with x1, and if I mutate x1, I also obtain something that it's compatible with x2. So if I mutate x1, I get this guy. That it's just like y. I have to mutate x1, so I have to look at my matrix. I have to look at the first column. And so I see a 1. So there's only going to be a 1 in a minus 1 in the second row. So that's why I have x2 to the 1 here. And then I have this expression. So x2 is compatible with x1 and also with x1 plus x1 plus x2 over x1. And here, then if I mutate this guy, again, I obtain this guy, and this would be the new expression. Then if I mutate this guy, I obtain this expression. and so on and so forth. And that's how I get this. And for example, this big expression, it's obtained by performing this non-trivial computation. So I have to take this trinomial to the cube, then add this monomial, and then it turns out that this big guy, it's all this guy here, and it turns out to be divisible by x1 plus x1 to the cube, and it's precisely this one. So an instance of the positivity of the Laurent phenomenon. And here, as you can see, I have exactly the same information, but it's a little bit more compact, right? So it's a little bit more compact. So here the cluster complex is an octagon. The exchange graph is an octagon as well. For example, in type A2, let me just put the cluster complex. So here, example, or in type A2, the cluster complex looks like a pentagon. The exchange graph, it's that one. How's the cluster complex? Exchange example, in type A2, the cluster complex, I have the variable x1. It's compatible with the variable x2. And if I exchange x1, I get x2, 1 plus x1. And if I exchange here x1, I get x1 plus x2 over x1. And I know that these are compatible to the long one. 1 plus x1 plus x2 over x1, x2. So this is the cluster complex. It looks like a pentagon as well. So this object and this object, in some sense, they are dual. So the exchange, for example, this is the, let me just put it here in blue. So if this is the exchange graph, this would be like the cluster complex somehow. It's going to be like kind of dual. Something of dimension 1 corresponds to something to dimension 2, and something of dimension 0, something of dimension 1 turns into something of dimension 0, and something of dimension 0 turns into something of dimension 1. So there's like some duality between these two objects. Here you can see exchange graph, exchange graph, exchange graph, cluster complex. Okay? Questions? Please ask questions. Any question, observation? Is it clear, or there are clarifications needed? Yes? This complex? This complex is going to be very important. In general, you see like this topologically, this is like a circle, right? This is also, so the graph, it's going to be, as you can see, the graph here is n regular. Here, like say, observation, the exchange graph, let's call it x of b tilde. The exchange graph of b tilde is n regular. So the exchange graph, you should think like a folding of the n regular tree. So the n regular tree, it's like where you put all your seeds, and then the graph, it's just like it starts to fold and produces a quotient of this tree and remembers the periodicities. The cluster complex is going to have higher dimension. Here, because we're like in dimension 2, both the cluster complex and the graph look like one-dimensional stuff. But a very interesting theorem is that a cluster algebra is of finite type if and only if its cluster complex is topologically equivalent to a sphere. So there's some topology here.
That is exactly the same with the Topology groups, right?
Exactly.
It's exactly the same. And when you consider the Salvetti complex, it's exactly the dual of the chambers.
Okay, let's talk. Yeah. So I mean, there's a bit of topology here. And the utility of the cluster complex, I mean, I have part of my research, it's, okay, I have a pentagon. How can I produce the cluster algebra out of a pentagon? So in my research, it's like, I have a paper in which I say, okay, you need the cluster complex plus some extra information to recover the whole cluster algebra from just its cluster complex. So it is possible to kind of construct these expressions using some topology and some algebraic geometry, right? Yeah, so, okay, let me continue. So we're almost there. I just want to finish showing the last example of associated to square matrices of size 2 by 2. So here, this would correspond to the matrix 0, 0, 0, 0. Right? So remember the theorem I stated in finite type, I was assuming that the quiver was connected, right? Somehow, I can also talk about connected matrices. So matrices that are not like, you know, like a block and then a block of zeros. This would be a disconnected matrix. 0, 0, 0 would correspond to, you know, the quiver 1, the disconnected quiver that has 2 vertices. If you compute, you know, the matrix associated to this quiver, since it doesn't have arrows, it's just going to have zeros everywhere. And here you can see the cluster, the seeds. So here it's x1 in the vertex 1, x2 in the vertex 2. I don't put arrows because there are no 2 arrows. If I mutate in 1, I replace this by this. If I mutate then in 2, I replace this guy by this guy. If I then mutate this in 1, I get this guy. And if I mutate this in 2, I get this one. So this is something of type A1 times A1. So here you can see all the rank 2 examples. We call rank, n is the rank. So here are the rank 2 examples. A2, which is a pentagon. B2, that it's an hexagon. C2, that it's also an hexagon. G2, that it's an octagon. And A1 cross A1, that it's a square. All of them are topologically circles, okay? For example, in the Kronecker quiver, for the Kronecker quiver, it will turn out that the exchange graph is just this infinite guy, just infinite strip, and the cluster complex would be the dual to this, so it's going to be like, again, something that looks the same, but it's kind of dual, and it's also an infinite strip. This is not S1. It's of infinite type. It doesn't close to a circle. Okay, so in the last 30 minutes, I want to link everything that I've just said to the case of the polygons, because the polygons were like very intuitive. Okay, so let's go back to the polygons. Before going back to the polygons, are there any questions? Yes?
You are here asking about the permutations.
Yes.
So I think the permutation like function is at like a function.
Yeah, so for example here, right, so if I have this one, x1 and x2, and I act back by the permutation 1, 2, right? So recall this is like, okay, so maybe this corresponds, maybe I should put this correspond to this vertex 1, 2, and the cluster x1, x2. So it's maybe easier to just see that there are 2 things going on. So if I act here by the permutation 1, 2, what I obtain, let's say I multiply by 1, 2, what I would obtain, it's the quiver that looks like I exchange 2 and 1, 2, 1, and then xi, it's replaced by, goes to x, the permutation I. So I will just take, I apply my permutation here. In 1, it's x2, right? And then I will apply my permutation here in 2, it's x1, right? Yeah, I mean, yeah, like you change, the arrow goes in the other way, right? And this looks the same. This looks like the quiver x2, x1. And if I see this picture, if I see this picture, and I see this picture, I say, of course, these are equal. Right? So this is an example of how the permutation is acting. It's acting on the vertices. What I'm doing here, it's like, also, if I'm in the matrix notation, I'm interchanging the first and the second rows and the first and the second columns. That's why the arrow also changes. Okay? More questions? Okay, so let me just try to link all that I have said with the pentagon, with the polygon, and also see why this gives me a global model of the cluster algebra. So that's very good, because we don't want to iterate, and we don't want to work locally. We want to have a global picture. Okay, that's the aim. We don't want we want to go local to global. So yeah, maybe I will erase here. So recall that, maybe I will just put it here, because it's going to be handy to have the construction available throughout the discussion. So let me just recall how the lecture of Thursday went. So recall, let PR be an R regular polygon. So last week, so if T is a triangulation of PR, then last week we constructed then polygon. Then we have a quiver QT. Okay? Let me just remind you this construction in an example, right? So how was it? Let's say a number less than 10. Anyone? A number bigger than 4 and smaller than 10. 8. Okay. N equals 8. For example, R equals 8. So I will have like, I will have like this. Oh, no, this is not an octagon. This was like, how do I draw an octagon? 1, 2, 1, 2, oh fuck. Yeah, I want this. 1, 2, 3, 4, 5, 6, 7. Okay, it's supposed to be regular. It's not regular in my drawing, but you know what I also, for simplicity, label this by this. Okay? By the numbers, 1 to 8, right? Now, let's draw a triangulation. Do you remember what was a triangulation? I have to take diagonals that do not intersect in the interior, maximally. So, give me one diagonal. Say a diagonal. Take me, for example, 2, 6. What? 1, 3. 1, 3. Another diagonal that is compatible with this one? 1, 4. Another one? 7, 5. Very good. Another one? 8, 4. Another one? I only have 2 choices. Okay, I will choose it. This guy. Okay? 7, 4. So how the construction went? I have to put frozen vertices in my edges, and I have to put mutable vertices. I should think as the diagonal as mutable vertices, and then essentially anytime I see a triangle in my triangulation, what I do is put like an oriented triangle. right? So here I would have, and it's clockwise. And it's going clockwise. Okay? So that would be the quiver. The quiver would look like, I don't know, it would look like this, 1, 2, well, this, and then I will have like, I mean, I can just forget the triangulation. I can forget the, I can forget the polygon. And yeah, it's, you remember that there's a theorem also saying that I can put or not put the arrows between frozen vertices because they will not affect the exchange relations. So they will not affect the cluster variables. So well, I would put them just to be good. So this would be my quiver, okay? Okay, just like to make it very explicit. This would be the quiver associated to this triangulation, okay? There you go. So the theorem I want to explain is that let R be greater or equal to 3 and T be a triangulation of the polygon PR. Then the cluster algebra A. Then first thing, the cluster algebra associated to the quiver of the triangulation. So for example, this cluster algebra is of type, is a cluster algebra of type A R minus 3, okay? You can see it here. Here, R it's equal to 8. R minus 3 is 5. I have 5 mutable vertices. And here, the type only depends on the non-frozen part of the quiver. The periodicity, the type, remember, it's about the periodicities and whether I have like finite or infinite type. So since the periodicities of this quiver and the one with frozens are the same, well, the type of the, let's say, the type is independent of the frozen information, so I just have to look at the mutable, and here I see an orientation of an A5 linking diagram. So this is why this quiver is of type A5. It's an orientation of this diagram, right? It's just like what I see. It's you know, these 5 vertices and an orientation of this graph. Okay, so this is kind of natural. That's not going to be obvious. Then, what is more interesting is there exists a bijection. Let's call it psi. No, let's call it H, bijection H, from the set of cluster variables associated to this quiver and the set of diagonals of PR union the sides of PR such that the frozen vertices, the frozen variables correspond to the sides of PR, okay? And yeah, so somehow clearly my bijection, you know, should be, you know, like any cluster variable should be associated to an arc, right? And the size should be the frozen variables. That's kind of clear from the construction. And maybe the second one, it's like flips of diagonals, clusters of this cluster algebra correspond to triangulations of PR and mutation of clusters, or let's say seats of then mutation of seats correspond okay, maybe it is such that it's like this bijection implies all these points. There's a bijection that satisfies all these points. Mutation of seats correspond to flips of diagonals. And and maybe the last point is that the cluster algebra A QT is isomorphic to the coordinate ring of the Grassmannian 2CR in so see it like this, okay? So I'm not going to give you like a proof of the theorem with all its words, but I'm really going to explain it and elaborate on the construction so that at least these points kind of are easy to believe, right? So it would be like a sketch of proof, okay? So questions about the theorem? Does the statement look correct? Let's try to understand the theorem for the case of the hexagon, okay? Let's take an example. Let's take the example, let's take R to be 6, right? So I'm working in an hexagon, and I would like to explain the theorem, okay? So, or see the theorem here. So I have an hexagon, okay? I have an hexagon, 1, 2, 3, 4, 5, 6, okay? So why I always get a cluster algebra of type AN or AR minus 3? Well, the answer is kind of simple. Any polygon has some distinguished triangulations. These triangulations where all the diagonals are attached to the same vertex. They look like a fan, like this one, right? If my polygon was bigger, I will just have like more diagonals, okay? So how does the quiver look like in this case? Well, in this case, the quiver looks like I have my mutable. And remember, the type only depends on the mutable part. It doesn't depend on the frozen part. So I just have to see what's going on here. So I will have to give like, you know, these oriented triangles. So I will just have these arrows, right? So if I have more vertices, let's say this is the vertex 1, this is vertex 2, this is the vertex 3, like in general, so on and so forth, and this is the vertex n, and then let's say this is n minus 1, then here the quiver will have all these vertices, and the arrows will be given in this way. So I see clearly an orientation of an A, of a diagram of type A, right? It's just like the directed orientation. Okay? Notice that there are more interesting triangulations, like this guy. For example, if I have this guy, the vertex will, the mutable part of the quiver will look like this, right? So this triangulation does not make it obvious that it's a quiver of type A. There are other triangulations, like this guy, like this one, that is not too obvious, that gives me a triangulation of type, gives me an orientation of an A, of a linking diagram of type A. But this one, it's always clear. That gives me an orientation, like the linear orientation of an A linking diagram. So this is kind of easy. No, this is the proof. This is the sketch of the proof. Okay? Here I can see it like in A6. Okay, it's right. So this should be easy. Now, how do I build the bijection? How do I build the bijection? So here I want this to be the initial cluster, x1, x2, x3, right? So I want, for example, that my bijection H, so here I will have like some let's say x. So this should be x, this quiver, 1, 2, 3. So I know that at least x1, x2, x3 are here. And well, I will also have like some others. I will have like this guy, this guy, this guy, this guy, this guy, and this guy. So I will also have like the frozens. So the frozens, I know, like if I number, I want this one to go to the sideway 1, 1, 2. This one I want it to go to the side 2, 3, right? So for example here, I have more, but I know that this should correspond to diagonals. These are of the form ij. Let's call this diagonal ij's, right? Such that so let's think that the vertices are in. Let's say that let's say like the vertices of the polygon are vertices of PR are identified with ZR, okay? So here I would have such that the difference between I and J, it's different from plus or minus 1, yeah, in the cyclic group. And here I will have the sides that are of the form I plus 1, right? This should be such that it's in set R, okay? So I know that, for example, this x1 should go to 1, 5. That x2 should go to 1, 4, to the diagonal 1, 4. Okay? 1, 3, x3 should go to the diagonal 1, 3. Okay? Question, and this is a question that you should answer. What should be associated to the diagonal 3, 5? So why did I put diagonal 3, 5? Because I can just put it here. This is the diagonal 3, 5. Okay? This guy is telling me that mutation of seeds should correspond to flips of diagonal. So I'm already giving you a hint. If I have this triangulation and I flip this diagonal, this should correspond to a seed mutation. Okay, so I see that this triangulation, this whole triangulation corresponds to this seed, the one that has this quiver and these variables. Now, if I flip this triangulation, then the most natural thing would be to mutate the seed in direction 2. Right? So what's the mutation of this seed in direction 2? So well, I will have now to, to put, okay? So I should have put names to these vertices. I could put like, 3, 4, 5, 6, 7, 8, 9, right? Let's do it. 4, 5, 6, 7, 8, 9, okay? So then I have this, this, and this. Okay, so I should mutate here at 2. So if I mutate at 2, I have to look at the arrows that are hitting me and the arrows I'm pointing towards. So who is looking at me? This guy and this guy, right? So it's x6 and x1, right? So here it should be x1, x6, and I should look to the vertices I'm pointing to. I'm pointing to 3 and I'm pointing to 7. So this is x3, x7, and I am exchanging x2. So the most natural thing is that I go map this to this. Okay? And so on and so forth. So how do I write this? I'm not going to write it, but as you can see, it's just an algorithm. So first of all, it might be better to change the labels. Don't use 1, 2, 3. Just instead of using x1, I use x15. If instead of writing x2, I use x14, because it's better, like in the Grassmannian example, to label the variables with this pair of integers, with these edges. So this is not the optimal. This is not the optimal labeling, but it doesn't matter. How would you write the algorithm? So just map the initial variables to the corresponding diagonals, and then algorithm. Suppose you already have an association of a seed with a triangulation, then the next cluster variable, if you mutate your seed in a given diagonal, in a given vertex, then the cluster variable, the cluster variable that you obtain will be associated to this new diagonal, just like this. Okay? So this would be just like the first recipe of the algorithm. What's the complication? What's the difficult part of the algorithm? For example, let's do this with the pentagon. So let me just show you a picture. It's a graph whose vertices are the triangulations of the hexagon. So you can see here I have an hexagon. Here I have an hexagon. So I have like an hexagon many times, and actually every hexagon has a triangulation, right? So what I have here, it's the graph of triangulations of my hexagon. So vertices are triangulations, and edges are connecting two triangulations that are related by a flip. For example, this triangulation and this triangulation are obtained by flipping this diagonal. If I flip this diagonal here, I obtain this diagonal here. And if I mutate this diagonal in this triangulation, I obtain this guy. Remember that flips, it's like an involution. Doing flip of a diagonal, it's an involution. For example, this is connected to this because if I flip this guy, then I obtain this arc, and if I flip this arc, then I go back to this guy. So just look at this picture for a second. Be convinced that what I have, it's all the possible triangulations of my hexagon, and that they are really connected by flips. The top part, not the bottom part, the top part, okay? So this is something that looks like the exchange graph. It's like the graph of triangulations. And actually, what this theorem will tell me is that a corollary of this theorem would be that the exchange graph of my cluster algebra coincides with the graph of triangulations of my polygon. So, getting back to the bijection, we want to associate to any cluster variable something. So for example, let's say I have, let's say I pick this to be my initial triangulation, okay? I know how to define my bijection. Now I want to know which cluster variable I associate to that arc. So my algorithm will say, okay, start mutating, and start mutating in a way such that this arc appears in your triangulation, okay? So what would be the idea? I have here, I'm starting with this initial triangulation, and I want to find a triangulation that has that diagonal. For example, this Y on the back has that diagonal. This one has that diagonal. Which other has that diagonal? These four are the four triangulations that have that diagonal. Do you see it? So I have to mutate this guy to any of those triangulations, and that would give me an assignation. But there are many paths that could link this seed, this triangulation, this one here, with these guys. There are many paths. I could start like saying, taking this path here, 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 and then I get some assignment. But I can instead start here and move here, then go here, behind, and then go here, and then I get this guy. Or I could go from here, here, and then get this one. So there are many ways in which I can connect the initial triangulation with a triangulation that has the arc there. So the theorem, so the complexity of the theorem, or say like the main difficulty in showing the problem is like this algorithm is well defined. It doesn't matter like which path I go, I will get to the, I will have, the assignment will be well defined. Example. And I will finish almost with this. This is my initial triangulation, and I want to know what's this variable. So for example, let's see an example that we're already familiar with, the A2 example. So I will write here like the 5 possible triangulations of the pentagon, and I will connect them by flip. So if I flip this diagonal, I get this guy. Then if I flip this diagonal, I get this guy. And then if I flip this diagonal, I get this. And then if I flip this diagonal, I get this, okay? So this is the graph of triangulations of a pentagon. It turns out that the graph of triangulations of a pentagon, it's again a pentagon. So for example, here, I know that this is x1, and this corresponds to x2. And for example, I want to have this, and I want this to be, you know, x1, x2, 1 plus x1 plus x2, and also that this is 1, this is 1 plus x1 plus x2, x1, x2, right? So I know that I can reach to this triangulation by mutating this and this. And if I do my cluster assignation, like if I do like if I see my pentagon, I see that I should assign this guy to this guy. Now, if I would go this way, I would also see that this guy should be assigned to this guy. So in my example, I confirm like the 2 paths going in this way are giving me the correct assignation, right? Okay, so I can see like how actually in my example the algorithm makes sense. Notice that this arc crosses the initial triangulation here and here. And somehow this has denominator x1, x2. This guy And for example, this guy crosses only x2. And this, by mutation, I know that this guy should be x2, 1 plus x1. And this guy is this guy should be obtained by mutating this guy. And this is, if I mutate it, it's x1, 1 plus x2, right? So somehow, I have an idea of how should the proof go. I should see that precisely the denominator vector is well defined. Like, if I have an arc, for example, this one should be a cluster variable that has denominator vector x1, x2, x3, right? So that would be an approach. That would be an approach just like focusing on studying denominator vectors. And so that would be like actually a proof that, an approach that can be made into a proof. I would have to see that all the cluster variables have different denominator vectors, and that the arc that crosses, I'm sorry, this is not crossing, this is, I'm sorry, this is crossing not in the interior, this is crossing in the endpoint. This should correspond to this arc, like, to the cluster variable with denominator vector 1, 1, x1, 1, 1, 0, right? So that would be a strategy of a proof, and actually it's like a good strategy. If you're really motivated, you can try to do this and try to prove the theorem. Let me tell you another strategy that would be successful. It's to use this point. Actually, one can use geometry to prove this theorem. What one should show it's that essentially this ring has a presentation, as I showed before. You know, many variables indexed by pairs, modulo Plucker relations. The Plucker relations are just going to be indexed by quadrilaterals, and then I would see like if I show this isomorphism, then I can show that any relation here gives an identity in this ring. So I'm just moving by identities in this ring, and that's why this assignment is well defined. So I don't know if this was clear or not, but like the message is like there's like a combinatorial way, and this is a geometric way, right? As I told you before, well, there are many ways to try to express cluster variables also. A combinatorial way, using this kind of combinatorics, or a geometric way, using this kind of varieties. So I hope, I will end up here. I hope that these observations help you believe that this theorem is true, right? And that you can also see like how there are different approaches, combinatorics and geometry. And finally, just see how this picture, it's already giving me global information about the cluster algebras, right? Because I can count now. I know how many seats this has. The cluster algebra of type A3 has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 seats. It has 13 seats. How many cluster variables it has? Well, as many as arcs. I have, I can draw the cluster complex. So somehow like the cluster variables would be corresponding to arcs. So here I have the dual complex. So instead of, like this pentagon here corresponds to all the triangulations that have like this arc, like the one, this guy, right? So this face here, where is it? Yeah, can be replaced by this vertex, by this vertex. So all the triangulations, no, not that one. Where is it? Okay. Okay, this is rotated, right? This is, yeah, maybe this one. Yeah, so I can do also like a dual complex in which vertices are arcs and adjacencies are, and simplices are just compatible arcs. So I have this arc is a vertex, this arc is a vertex, this arc is a vertex. This edge, I put it here because because this arc it's compatible with this arc. This edge it's here because this arc is compatible with this arc. I have this edge because this arc is compatible with this arc, and I have this triangle, the two simplex, because all these three together are compatible pairwise. So I have a two simplex. I have 0 simplices, 1 simplices, 2 simplices, and here I'm depicting an arc complex where the vertices are arcs, and simplices are sets of compatible arcs. So the theorem here, a corollary of this theorem would be like the exchange graph will correspond to the graph of triangulations. The cluster complex will correspond to the arc complex. And I can perform countings in cluster algebras by just doing combinatorics. I know that I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 cluster variables. I have 13 seeds. I have also, as you can see, this is so beautiful. As you can see, this guy is formed by pentagons and the squares. And pentagons are of type A2, and the squares are of type A1 cross A1. And as you can see, you can think of this pentagon as all the clusters that contain a given diagonal, say this guy. So it's like freezing that guy. And we know that if we freeze something, the periodicities are the same as in the non-frozen part. So the non-frozen part would be an A2. So I just have a pentagon. That's why I have a pentagon. And I have here a quadrilateral because I'm just looking at all the triangulations that have this arc in the middle. So if I freeze it, then I just have an A1 kind of thing because I just have these two disconnected vertices. Where they are connected by something that it's frozen, but I mean, I just forget the frozen and I just get two disconnected vertices. That's why I have here a quadrilateral. This is of type A1 types A1. This is of type A2. And now you can imagine that if you take an heptagon, then you will obtain like a graph that is obtained by gluing things of type A2 and A2, A2 times A1, A3. So A3 will be pasting this kind of, we call it a sociahedra. The sociahedra, so it will be something very complex, but very beautiful. And you can perform counts. So the exercise would be to use this theorem to count how many, so exercise, use this theorem to count the seeds and cluster variables in a cluster algebra of type A, in a cluster algebra of type AN. Now it's possible. Now I have a global model, right? I have 9 seeds and 13 in type A3. What about A4? What about A5? Okay, I will leave it here.